All right, welcome to Module 16 on scaling, encoding, binning, and feature creation. This is where we are going to increasingly start taking the raw data and converting it into a form that will help us and make downstream processing and analysis a lot easier. So I'm assuming that you've already played around with pandas a little bit, with data frames, possibly with series and indexing. So you've gotten the code that I've provided and you've played around with it. You've done a little bit of cleaning, so you understand things like missing values and duplicates. I'm not assuming that you have prior experience with scikit-learn. Scikit-learn is another popular Python library that's used a lot in kind of machine learning, traditional machine learning especially. We're going to gradually use more and more of it over this course. I also can assume that scaling and encoding, the kind of topics that we'll be discussing today, has been done for you in the past, but it has been done sort of behind the scenes by libraries like pandas and NumPy. I'm going to talk a little bit about training and test splits and data leakage. So this might be new to you, and we'll kind of pass over it today, but we'll come back to it in a future module to kind of complete our understanding of it. We're still going to use some tiny data sets that mimic realistic use cases, just so that we can run things easily in this theory. So by the end of this module, you should be able to diagnose when scales, like the widths or the variety of data you have in your variables, and the encodings, or the representations of that data, could either break a model or mislead a model, or make modeling or understanding the data incorrect in some way. You'll be able to implement simple scaling and one-hot encoding. I'll define that later. And binning, I'll define that later also in pandas. And you'll do that in a way that helps also ensures that this information is not leaked between the training tests splits that I mentioned earlier. We saw this a little bit in Module 11, but you'll be able to create new features that capture useful information about the world, in this case the data generating process we've been calling DGP. So you'll be able to engineer new features. You'll be able to explain just in language how choosing features can affect things like distances, decision boundaries, and error costs. All of these topics we'll get more and more into in future modules, but we're going to get exposed to it a bit today. And you'll also, as usual, identify kind of situations of ethical risk. So before we actually get started, before we actually start doing something like modeling, we need to figure out what similarity means, or what it means to say that two data points are similar to one another. If I want to say, these two customers are similar, therefore if one buys a product, I think the other one will buy a product. Or if I want to say that these two patients are similar, so if like one patient has a disease, the other one might have a disease or be at risk of that disease. Like, what does similar mean in those two cases? So normally models don't have direct access to the world. We provide data gathered from the world to our models that basically just see tables of data. It could be numbers, it could be nominal data. But for the time being, we're talking about numbers. So like there's some data recorded numerically from the world, and that's what we have available to us, the data scientists, and that's what we're going to provide to our models. So before we have a model to make predictions about customers who might buy things or patients who might have diseases, we need to figure out which features actually exist in the first case, how large the differences are, and what large actually even means. Right? So what counts as these two data points are close to each other, these two are far from each other, maybe there's a third category, kind of mediumly far. And then we'll also need to be kind of thoughtful and smart and try to figure out what details are going to matter to us and what details won't matter to us. All of this, so making these decisions, these choices, are what we call feature representations, or they're part of feature representations. So in practice, making choices on what features we're using can matter more than the choice of model itself. In fact, I'd say a lot of the time that's the case, right? So you might come with the fanciest neural network model that you can think of. It was just released last week and it's the fanciest thing that there is. But if you don't give that model anything useful, it's not going to be able to make good decisions. This is the kind of the garbage in, garbage out model. You want to make sure that what you're providing to the model, whatever it is actually of high quality. Okay, so we need to represent the data well. So this module will focus on scaling, encoding, binning, and feature creation, which is part of feature representation. So why does preprocessing matter? Let's consider this small credit union. Okay, maybe both of us. We're helping a small credit union decide which loan applications to flag for manual review. Okay, so we have from this credit union some data in a table of all the loan applications that people have put in. So we have something about the demographics of the applicants. We have their age and years. We have their monthly income. Maybe we're more likely to give a loan to someone who has a higher monthly income or vice versa. There's a debt to income ratio. How much debt does someone have relative to their income? What is their employment status? This is a category. So they could be a student, or they could be part-time or full-time or unemployed. What city are they in? Halifax, Truro, Sydney, these Nova Scotian cities. And a binary variable defaulted. So it's 1 if they've defaulted on a previous loan, otherwise it's 0. So all these applicants come in, and we want our model to just flag some of these applications to say, well, we need extra human review before we grant these. Okay? And as usual, there's going to be a thoughtful trade-off we have to make between the errors that we can have. So again, there's false negative errors and there's false positive errors, and each of these are associated with different kinds of costs. So if we make a false negative, if we think somebody is not risky, but they actually are, so they are a negative, but we falsely say, we think they're a negative, but that's false, then we miss that. We give them a loan, they don't pay it back, we take a financial loss. So the cost is kind of obvious. What is a false positive? A false positive is where the model says this person needs to be flagged, it's a high risk, but that's wrong. So we're over-flagging safe borrowers. There's risks there, so at least the customer gets annoyed. Maybe we have to put the people who work at the credit union, we have to use their time to analyze things, to interview the customer, to dig deeper into the data. All of that also costs money. And so there's costs associated with false positives as well. So for now, we're not going to build that classifier. So we're kind of still building towards the modeling step by step through these modules. But we want to shape the data in a way that any model we build in the future will be able to learn how to do this task effectively. And when I say effective, I mean robust to all kinds of different data inputs, and also fairly. So there's these 4 ideas I mentioned earlier. Scaling. This basically takes numerical features and it kind of stretches them or squishes those features so that they're on comparable ranges. Encoding can mean many things. In this case, it means taking categories or labels, which we represent as text, and convert them into numbers in a way that's meaningful. We'll have binning. This is taking continuous variables, so variables whose values are on the real valued scale, and converting them into ordered categories. So age might be something we have in terms of years or months, but we want to break that into segments in time. And then feature creation generally is constructing brand new variables that better reflect what we're looking for. Maybe the high-level data or the data we obtain itself is not sufficient, so we need to kind of apply some small little functions that kind of distill or pull out useful information for our decision-making process. So you can think of this as sort of a coordinate system in which the model is going to make decisions. This combines scaling and binning. Here we have these 5 data points that coincidentally look like Cassiopeia. Regardless, we have these 5 data points, and each of these data points is represented by a couple of numbers. We have feature 1, whatever it is, that's one number, and feature 2 is another number, whatever that is. That's our x and y axes. So the first thing that's going on here is like, we don't necessarily know what the original scales are by looking at this graph. So as you can see down here, it says feature 1 is scaled income, right? So the people applying for these loans might be making $0 a year. They might be making $25,000 a year. They might be making $50,000 a year. Okay, they have a wide range of these numbers. But we've taken all of these possible numbers for these 5 applications over here, and we've kind of moved and squished them so that all of them fall in the range of -2 to 2, and sort of the mid-range of all of these values is 0. Okay, so obviously, hopefully anyway, someone's income is not going to be -$2 a year. We've scaled the original units on dollars down to a scaled unit, -2 to 2, which doesn't necessarily carry the exact meaning of dollars. The ratio we've also done similarly. We've scaled from -2 to 2, and we've moved the data up and down in this range so that the midline is at 0. So that's scaling. Binning is represented by these grids over here. Okay, so we've kind of split this range, this Euclidean sort of space, into 4 quadrants. And in this first quadrant, we have 1 data point. In the second quadrant, we have 2 data points, and so on. So now we're doing the binning. Now we can say, well, these 2 data points in this quadrant are similar in some way. These 2 applicants have a scaled income, bigger than the midline, and their debt ratio is also above 0. So they're similar in some way. So we just group them together and we give them some kind of category. We can name this anything we want. We can literally just call this, Q2 for the second quadrant. But now we have some information about these applicants, and we can replace these kind of coordinates, which are like specifically 2 numbers, right? So this data point over here is -1.5 in the x-axis and 1.25 or so in the y-axis. We can replace those 2 numbers with just 1 label, quadrant 1. That's what we call binning. Each of these represents a bin. So again, here's our kind of pipeline. We start with the raw data. We clean things up. We look for missing data and duplicates. We do a little pre-processing. This is where we are now. We're going to do some scaling, encoding, and binning. And once we have that, once we've prepared the data and made it ready for our model evaluation and training, that's when we get on to the next exciting phase. And then finally, again, the end is never lost. We're always aiming towards helping people make real decisions in the real world to make the world a better place. We're going to get there, but we need to make sure that each of these preceding steps are done correctly. So here's another anti-example. This is where encoding sort of goes wrong. So imagine we have employment status. This is part of our data set, and this is basically just a set of 4 different labels: student, part-time, full-time, or unemployed. And it can be tempting to just replace these textual labels with numbers. We have a spreadsheet. We have all these different kinds of data types in the spreadsheet. For whatever reason, we want to convert data into integers or into numbers. So I'll just replace every instance of the word student with a 0, and every instance of the word part-time with 1, and so on. Okay, and that seems fine. So I've replaced labels with digits that represent those labels. Okay, and as long as I'm careful, this isn't bad. I have kind of wasted time a little bit. Like I haven't really gained anything by doing this, but this can also lead to problems because now these, if you're sloppy, you can look at these numbers, these 0, 1, 2, and 3, and think that there's some kind of ordering going on here. Obviously, there's an order to numbers, and it kind of implies that, well, there's an order from student to part-time to full-time to unemployed. Right? There's an actual order of these labels, but there's no order to these labels. The labels are nominal categories. They could have come in any order. So the mapping to numbers is sort of arbitrary. So the first thing is the order is meaningless. The second problem is that there are distances between numbers. Right? We talked a little bit about ordinal categories in an earlier module. It's important to remember that, but if you forget that for some reason, then you'll look at these numbers and say, well, there's, the difference between 1 and 2 is 1, and that's the same as the difference between 2 and 3, which is 1. So in some sense, the difference between part-time and full-time is the same as between full-time and unemployed, right? And already this is sort of nonsensical, like at least with our understanding of employment, like these distance measures don't seem to map out. So we've fallen into another trap of replacing labels with numbers. If a model is using Euclidean distance, right? So the distance between 2 points is just like a straight line between them. We'll talk more about vectors soon enough, which I'm also excited about. If we're measuring Euclidean distance, the distance between 2 points, unemployed is the furthest away from student by the way we constructed things. And is that also the reality? Maybe like being a student, is similar to being unemployed because you're supposed to be spending your time, studying and restudying and doing exercises and learning and becoming a full member of society and so on, so like you can become a full member of society while being employed also, but the idea of being a student and the idea of being employed might be somewhat different than each other. They're separate. So like why is unemployed and student so far from each other? It's going to be, this is the solution now. We're going to one-hot encode each of these labels. Okay. So a one-hot encoding is basically a vector, a list of numbers. All of them are going to be 0, except there's going to be a 1 in an index that represents that category. Okay, so in this case, picture a list of 4 digits. Picture all of them are 0, but there's a 1 in the first spot. That first spot represents student. So whenever you see the word student, you can change that label to a 4-digit vector, which is 1, 0, 0, 0. Every time you see the label part-time, you'll also change that into that same 4-digit vector, 4 spaces. But the second, this is a second label, so the second index is going to represent that second label. So part-time would be represented 0, 1, 0, 0. And similarly, unemployed would be 0, 0, 0, 1. We'll see why this makes sense in a moment or two. But one-hot encoding is sort of the fundamental way that we represent a ton of things in machine learning. In fact, the words that you type into large language models are split up into sub-word components. And those sub-word components are then represented as these one-hot encodings. So a little bit of math. Z-scores is our first means of doing scaling, and it's probably the most robust and the most commonly used form of proper statistical scaling that uses some aspect of the data to tell us what the scale should be. In fact, the example I showed you earlier with those 5 dots, centered around 0, that's an example of Z-scoring. So the intuition behind Z-scoring is we want to measure how many standard deviations away from typical, or average, a value is. So here's a formal definition for a feature x. We have some variable x, let's say the x-axis we saw earlier. What is the average of those values? Well, here it is. We know how to compute the average of something. It's just the sum over all instances we have, all data points we have, all n of them. We just add up all of their values and then divide by the total number of values we have. That's the average. Okay, that should be well understood. I do expect that most of you ought to know what standard deviation is, but this is less likely to be something you need to memorize. But it's just the squared difference between every data point and the mean, summed over all data points, the average of those, and then the square root is the standard deviation sigma. So here's the standardized value. This is what we call, this is how we can convert a data point to have its standard scaled version. We take the original data point x, we subtract the mean from it, right? So that's kind of like moving the data over to the center. So if this first step, if the mean is 2 and x sub I is 3, 3 minus 2 is 1, we just kind of move that 3 value over to the 1 value. We're not quite finished yet because now basically all of the data has just kind of shifted left or right. So we're centered around the mean mu. But we also want to squish everything. We want to squish it so that all of like the first standard deviation will be 1 unit away from the mean. And to do that, we just divide by sigma. This is one of these important fractions or important definitions. I ought to put a box around it, but you can put a box around this when you're taking your notes. There's many ways that you could memorize this. This form is super simple, so I tend to suggest to memorize something like this formula, the z-score. Just write it down a few times on paper until it becomes like muscle memory, but also try to understand what's going on here. We're just shifting everything according to the mean, which is the numerator, and then we're dividing everything by sigma to get everything relative to the standard deviations. So here's a little bit of an example. We have the people we have in our data set. We have incomes for them now. This is our kind of case study. So person A has a raw income of, say, $2,000 a year. What is the average of all of the raw incomes? So we have three values of x, 2, 3, and 4. How do we compute the mean? It says 4 plus 3 plus 2. So that's 9. What is the average of 9? 9 divided by 3 is 3. So the mean value mu for this variable x, which we all call raw income here, is 3. Mu is equal to 3. And then when you see what's going on here, well, I'm taking 3, I'm subtracting the mean from it, so the actual value of x sub 2 here is 3. Subtract mu from it, 3 minus 3 is 0. It kind of doesn't matter what sigma is. When I divide by it, I'll get 0. This is the z-scored version of B. I'll leave it as an exercise to you to kind of go through the steps and make sure you get these same values over here. If you get different values, it's possible that I made a mistake, so feel free to let me know in the teams for this class or in course when we meet. So here's we've taken our raw data and we've just kind of scaled it, right? So person B is very typical. They're exactly the average income. Person A is a bit below the average. Person C is a bit above the average. This is kind of obvious to us in this toy example, but you can imagine how if you have hundreds or thousands of rows, how suddenly seeing things scaled this way will start to give you some intuition. It turns out here that A is 0.7 standard deviations below typical, and C is 0.7 standard deviations above. Here's a little visual for z-scoring. This is basically like the distance from the mean and standard deviations. So here you can see this is like a bell curve, a normal distribution that represents the data. So I've taken the data, I've shifted the mean of the data, I've shifted it over to 0. So now mu is kind of lining up on 0, and then I've kind of just moved this Gaussian curve. I've squished it like inwards, or I've stretched it outwards, so that one standard deviation is one scaled unit away from the mean mu, and then I have the kind of distance. So I have a particular data point x, and that's represented as the distance between mu divided by sigma. So this x is going to give a positive z-score, and it's going to be something looks like above the value of 1, obviously. So the note here is that scaling your data with a z-score is essentially like fitting a normal distribution to your data, and then moving it over to have 0 mean, and then stretching it so the standard deviation is 1. That's the first kind of scaling. Here's a second kind of scaling. It's called min-max scaling. We're going to, in this case, scale the data to be on the range of 0 to 1. The intuition here is that we're going to stretch or compress the feature values so that whatever the minimum value is, that's going to be 0, and whatever the maximum value is, it's going to be 1. So here's the formula for this other kind of scaling. For any data point, x sub I, in my data set, I'm going to subtract out the minimum value, and then I'm going to divide by x max minus x min. Okay, this is kind of similar in the form to what we saw a moment ago with z-scaling, in the sense that it's like x sub I minus something divided by something that scales things. Same idea. We shift things and then we scale them. This numerator, the top part, basically takes all of the data and sets it so that the smallest value is at 0, and then the denominator is just the difference between the previous maximum and the previous minimum. That gives me the range, and the dividing by that range ensures that everything is going to be on the scale of 0 to 1. So When would we use this? Well, for algorithms that all features are in a similar range, like they're distant based, you could use this. For visualizations where we want features to be comparable and not be squished too much, just shift it over, that will be fine. There are some problems though, right? So we have some set of data. On that data, we have a minimum value and a maximum value, so we get our mins and maxes. We could then scale all of our data according to mins and maxes, like I showed you a moment. But what happens later on if a new data point is collected, it occurs, but it's less than the previous minimum, or it's greater than the previous maximum? That new data, by definition, will either be negative or more than 1, which will be outside of our range. So if we have some logic in our code that assumes that the scaling will always give something between 0 and 1, then this new data that has happened to be sampled outside of the original sampling range can potentially cause some problems. We might see some issues of that, some examples of that later. There's ways to deal with it, of course, like you can always clip things. So if a new data point is bigger than the previous maximum, you can, this is kind of cheating a little bit, but you can pretend that that value is whatever the previous maximum was. So you'd clip at the previous maximum. I think there's probably smarter ways you could go about doing that. You might want to think of different alternatives on your own, but you understand the overall idea of what we're trying to accomplish. Here's a visual example of what we're trying to do. So here's the original income data. So this is the raw data over 5 data points, ranging from a bit less than 2,000 to approximately 8,000 or so. So the previous minimum was this value on the left, and that now becomes 0. The previous maximum was 8,000 over here on the right. That now becomes 1. And then everything else is kind of just compressed on that scale. So this scale is no longer income. I can't represent this as Canadian dollars anymore. It's scaled, so it's not on that same scale. It can't use the same units. But like the distributions are identical. If you were to cut this image out and superimpose it on the one on the left, it would fall in completely. Like all the data points have been scaled totally linearly, right? It's just that the values of the actual numerical values have changed, but their positions on that scale have remained the same. So those are 2 forms of scaling, z-scoring and min-max scaling. Now I want to encode my labels, right? So employment status, student, part-time, full-time. I talked about this a moment ago, and I gave you an example verbally of it before, but here it is visually. Okay, so it essentially represents every category as its very own binary yes/no column. Like, is this person employed as a student? 1 if they are, otherwise 0. Are they employed as part-time? 1 if they are, 0 if they're not. Are they employed full-time? 1 if they are, 0 if they're not. So you can see how if these labels are all mutually exclusive, you can only be one of these things at a time, then only one of these elements in my list will be 1 and all others will be 0. So someone who's part-time, are they a student? No. Are they part-time? Yes. Are they full-time? No. So part-time becomes 0, 1, 0. So this helps to avoid sort of numeric orderings and lets models learn arbitrary patterns across categories. I'm going to jump to another browser for a second. Great, now here we are in another browser that can display this image properly. So we talked about converting labels into one-hot encodings. And here's just basically what this looks like geometrically. See, we have these points. So a student is represented down here. It's 1 in the student dimension, and it's 0 in the full-time and part-time dimensions. A part-time person is going to be 0 in the student dimension, 1 in the part-time dimension, and 0 in the full-time dimension, and same for a full-time. So this is sort of like, because these dimensions are all orthogonal to each other, they're all at right angles from each other, this is like as far away as these points can be from one another. And each of these dimensions sort of encodes one aspect of the variable I care about, and any data point I have is going to be represented as one of these points. The labels are going to be these points anyway. Okay, so I've made them maximally different from each other. There's some interesting theory around this also, but you can kind of see what's going on here. Okay, so all of my label student is going to be 1, 0, 0. All of my label part-time is going to be 0, 1, 0. So imagine that we've been measuring things precisely. We've been measuring income in dollars and Canadian dollars. We've been measuring things in years. We've been measuring distance to the nearest store in terms of kilometers. But so far we've been talking about things like, well, I'm going to scale things down into by min-max, or I'm going to do a z-score, and I'm going to kind of just throw away the units of measurement that I've been using and have some new unit of measurement in which everything is scaled between 0 and 1. So like the actual number of kilometers or the actual number of years is sort of evaporated in some sense. Like, why would we do this? Like, why would we round the data? Why would we like bucket our, say, age into quadrants like we saw right at the beginning? And why would we bin things? This seems to be counterintuitive. So, we seem to be throwing away precision. It might, it's better to know that someone is 26 and not 25 than just knowing that they're in their 20s is our intuition. So before we answer this and why we're going ahead and doing these sorts of binnings and these sort of representations, we need to just take a moment and consider, well, is extra precision actually giving us more information, right? Like when I scaled those 5 dots down from the on the range of dollars, Canadian dollars, down to just a range of 0 to 1, have I actually lost any information that might be useful for me to do machine learning on, right? Like the order is preserved, the relative distance between data points is still preserved. So what does it matter if it's on dollars or on 0 to 1? Can extra precision amplify noise? Right? If one variable is on the order of thousands of dollars and another dimension is on years of age, can that disparity cause problems for the model? Is it ever the case that coarser features might actually be more meaningful to us? Right? When might that be the case? We will answer that over the course of several modules, but I want you just to think about it for a little bit to get your own intuition at this moment. So this binning is not a mistake, but it is a bit of a trade-off, and we'll talk about it in the next section. So finally, we're going to talk about this binning idea. This is very similar to the quadrants we had initially. Sometimes the exact value, so 41 versus 42 or 25 versus 26, that might actually not matter that much. Maybe we actually coming up with aggregations, like we've been doing in several other Python examples, actually has been helpful, like to group things together into meaningful chunks or collections from which we can take some analysis. So age originally could be on a scale of years, and I'm going to convert it into this. So anyone 18 to 24 is young, anyone 25 to 44 is mid, and anyone 45 years or above is a senior. Maybe this is not correct. This is a decision I've made. This is like assumptions I've made. We document our assumptions as always, but here our assumptions are encoded. And now we can look at some data. So here's like a distribution of data over years. So we have, this is just a count. So we have, 6 people between the ages of 18 and 19. We have 3 people between the ages of 22 and 23, and so on, all the way down the range over here, right? So we've taken our bins that we mentioned a moment ago, and we've split things up. So all of the individuals down here in green their age would be replaced with the label young. All of the individuals over here in orange would be replaced with the label mid, and so on. Okay, so I've taken all this sort of messy, bumpy data, and I've converted that messy, bumpy data into one of 3 labels. There are some risks, and you probably already thought of a few of them. If these bins are too wide, we've lost some signal. Okay, so there might be some obvious reason why someone less than 24 is different than someone who's 45 or above, or certainly 70 and above. But if we have a range that covers that entire spectrum, then we've lost, whatever differentiates those groups. We put all those people into one big group. So we've lost meaningful precision that way. We've lost the signal that way. If the bins are too narrow, then we've kind of overfit a little bit too much, and then we've got too sparse data, right? So the difference between someone who's 22 or 23 versus 24 or 25 might not matter that much for whatever our use case is. But then we suddenly grouped, if our bins are very narrow, and the first is one group and the second is another, then we've said there's a difference there. Maybe there's a difference, but the problem now is I only have 3 examples of people in that first group. And 3 examples is not normally enough to compute reasonable statistics. So I wouldn't be happy then either. So there we go. If we bin in this way, if we decide like we've set these ranges that young is anyone up to the age of 24, and we've done that on all of the data we've had, but then later on in the future, maybe when you're reviewing this module in the future, you take some data to build a model to understand age ranges, and then later on you want to evaluate whether it's a good model or not on some other data. If I've used all of the data, including that second set, to compute my ranges, to compute my bins, then somehow information from my test set, my evaluation, has leaked into or snuck into my model. And that's one of the main cardinal sins, I guess you could call it. The main big problems of machine learning is when I'm taking data that I really shouldn't have access to yet, and I'm using information there, no matter what that information is, even just seeing it with my eyes, and then somehow using it, even subconsciously, in defining the model beforehand. So we'll talk more about that kind of challenge later, but there's an instance here where leaking data from test into training could be a problem. So let's go through an example. We have our tiny credit data set. Again, this is a fictional data set defined here and shown here. We have loan ID, we have ages, monthly incomes, depth to income, and whether or not they've defaulted. We talked about this data set earlier. Okay, we have units in years, Canadian dollars, a ratio on 0 to 1, and binary. So we want to maybe inspect some scales. So when you have a data frame, you can call the describe function. And here we're just going to include everything. So we have the parameter include equals all. And then what we get is this big table over here. So we have counts, averages, standard deviations, and so on. We have 10 different loan IDs. The average is 5.5. The standard deviation is 3.02, and so on. You can ask yourself, is that meaningful? Is the average of this column, loan ID, actually conveying any useful information? Maybe, maybe not, but certainly hope you'd agree that the average of the loan ID, this first digit over here, might not be as informative as the mean of age, right? The average age of someone applying, which is, by the way, 38.1. So we have counts, means, standard deviations, the minimum. And then we have values at these percentiles. So if you were to take all of the data and sort it and take the smallest 25%, what is the value we'd expect to see at that 25% marker? That would be 30, right? So 25% of the data is 30 years of age or younger. 50% of the data is 37 years of age or younger, and 77% of the data is 44 years of age or younger. And the oldest applicant we have is 60 years of age. So a couple of things to notice. Monthly income over here is in thousands of dollars. Debt to income is 0 to 1. So these statistics are all kind of over the place. There's a big difference between 3,950 and 0.6375. So already we're starting to see some differences that are very telling between these columns, between these variables. And if we're looking at distance, so how different are individuals, these data points? Well, the distance between 0.5 and 0.55 in the debt to income ratio is very small. The difference of tens of dollars even, or dozens of dollars between two applicants is going to be orders of magnitude bigger, all right? So 10 is an order of magnitude bigger than 1, so these differences are going to be amplified if I'm looking at monthly income. But does that really mean that the differences between these two data points are meaningful? It's not necessarily. The differences come down to just the happenstance of the units we happen to have been measuring these variables in, right? Age is going to be on the span of a few dozen. Income can range over thousands. Debt to income only over 0 to 1. So if I'm looking at the distance between these points, units matter. I think that should be obvious at this point. So we can visualize a couple of things. Here's just looking at these variables. We've looked at matplotlib and plotting histograms quite a bit already, so no need to get into the weeds there. But here's the distribution of monthly income, and here's the distribution of debt to income ratio. Okay, there's not too much data here, which is why these figures are so blocky. But you can see a monthly income is sort of tilted towards the left, below 3,000, and here there's kind of this distribution where there's kind of two bumps to it. Okay, so far, like you can see that like the distribution, the range over here between 0.3 and 0.8 is way smaller than between 2,000 and 7,000. But the distance between the minimum and the maximum maybe ought not be dependent on the units of measurement. So we want to train a model. So we haven't really talked too much about what training really means yet, but I'm going to rely on your intuition for the moment. I'm going to take some of our data and only take a subset of it and leave the rest out. We're going to come back to that other held out data later, and we're going to use that data to evaluate how well we're doing. Okay? I'm going to just, can I do this? There we go. So we want to understand what's going on in the data. In other words, we want to model the phenomenon that's described by the data, and we call this training. So for now, I'm just going to take, the first 7 data points. So, data points from index, the beginning all the way to 7. There's a :7 here, which just means like everything from the beginning up to index 7. And then I just copy it into this new variable called train. And then similarly, everything that comes after 7, copy it into test. When you download this and run it, I want you at line 3 to just print up train and test to make sure that the correct rows are being copied. Maybe I made a mistake here also. I want you to tell me if I made a mistake or not. But assuming I haven't, let's just look at the numerical columns. So the numerical columns in my data frame are called age, monthly income, debt to income. These are these 3 strings. And now I can start taking means. I can take means over numbers, so I can take my training data. I can take only the numerical columns, and then for all of the numerical columns, I can compute the means. And then I'll store that in the variable called train_means. I can also similarly compute the standard deviations. I wouldn't worry too much about what DDOF equals 0 means. This is the degrees of freedom. You can ignore that for now. But this gives me the standard deviations over my 3 numerical variables. And then just print it out. So here's what I get. The first one is age. The average is 38.57. The average of age is 38.57. The average of monthly income is about 3,500, and the average debt to income ratio is 0.47. I also have the standard standard deviations and train standard deviations here. That's these 3 quantities over here. Each of these are floating points. So the mean, when I'm computing the mean over something, you're taking you're summing and you're dividing by another number. Often this translates not into integers but into floating point real values. So Python goes ahead and stores these as floating point numbers, which is nice. So now we're going to just scale using only the training data. So this is what we talked about when we're talking about leaking information. I've kind of taken indices 8, 9, 10, and I've held it out, and I'm only dealing with indices from 1 to 7. That's my training set. That's the set of data that I'm allowed to use to compute some statistics and to figure out what my scaling should look like. So here I'm only using I'm taking a copy of the trained data and a copy of the test data, and I want to scale both of them. So it doesn't make any sense for me to scale thousands of dollars in the income dimension down to say 0 to 1 in the training set, and then leave the test set on a dollar scale on thousands and thousands. I'm also going to have to convert the test set into a 0 to 1 scale, but I'm going to do that only using information I have on the training data. Okay, so I'm going to be doing, a bit of you can pause right now, or you can take a moment to look at line 4 and tell me whether or not this is a z-score or whether this is min-max scaling. Hopefully it's going to be obvious to you what's going on over here, but this is z-score scaling. So here all I'm doing is taking all of the data I have in my train set. I'm subtracting the mean from it, which I've computed previously, only on the training data. I divide by the standard deviations I have obtained only on the training data, and that gives me my scaled training data. I also want to scale the test data, like I mentioned a moment ago, but I have to make everything sort of in the same dimension. It doesn't make sense to scale the training data into a training scale on 0 to 1, or on a scale relative to the training data, and scale the test data on some other scale, because those two scales will not coincide with one another. They'll be on entirely different spaces with different means and different standard deviations. Rather, I take the test data and I'll scale it according to the statistics I've obtained on the train data. Okay, so that's what's happening here on line 5. Take all your test data, but then remove the training mean and divide by the training standard deviation. So scale so the test data is in the same dimension as the train data. And then I'm just going to, here we go, just to take a look at things again and take the scale of the training data and then describe it. And that's what I get over here. This is just like, again, the describe function gives me some high-level statistics, which you saw a moment ago. So some quick sanity checks. We know that if we're doing z-scaling, the average should be 0 by definition. And then the standard deviation should be 1 by definition. Is that the case? Are the training means of the scaled features close to 0? Are the training standard deviations close to 1? I welcome you to look at these numbers and answer this question on your own. I should not assume this necessarily, but I hope you know this already. E followed by a number means times 10 to the power of that number. Okay, so 1 E minus 16 means 1 times 10 to the power of minus 16, or 1.1 divided by 10 to the 16, a big number. Okay, so the bigger this number that you're dividing by, the smaller and smaller, or the closer and closer this number is going to be to 0. Okay, I hope that makes sense. So like 1 E minus 2 will just be 1 divided by 100. 1 E minus 3 will be 1 divided by 1,000, and so on. So I hope you realize this. E is just sort of an engineering way of saying times 10 to the power of. Anyway, so here's our code just to kind of confirm these sanity checks. We'll take the scaling data, we'll take the numerical columns, we'll compute the mean. We kind of saw that already from this description. We'll round, to the nearest 5 decimal points, and we'll also, look at the standard deviations. And here's our statistics at the bottom. So let's visualize before and after. So we've previously scaled everything. We're just going to go ahead and plot it. So we took the training data, the monthly income and the debt to income ratio in the original training space, which is going to be dollars versus 0 to 1. And we've taken the, down here on line 8, we've taken the scaled data, the scaled monthly income and the scaled debt to income, and we've plotted all of those. Okay, everything that we've scaled should maintain its overall shape. And like we saw earlier, you could just cut this image and superimpose it on the other, and they would line up perfectly because everything has been scaled uniformly, like linearly. But as you can see, as before, the scales are all different. So the monthly income no longer goes from less than 2,000 to a bit over 7,000. Now it goes, in this case, from a little bit less than -1 to up to 2. Okay, and then the average of all of these data are going to be around 0, which I'm indicating right now. Okay, what does it mean for this data point to be all the way over here at 2? Well, we know what scaling means. We know that the scale in the z-scale basically just means the number of standard deviations away you are from the mean, which all that means is that whoever had this income of slightly over 7,000 is 2 standard deviations away from the average. Okay, are they far from the average? Are they close to the average? The scaling down here basically tells us that distance. So before, when we're combining these two variables, the income, here we go again, let's zoom out. There we go. When we're comparing these two variables, the x-axis just totally dominated this difference. So the difference between this data point here and all these other data points would be just like totally overwhelmed by the difference between approximately $5,000 and over $7,000. But when we scale everything down, then suddenly we can look at these data points kind of visually, like actually makes a bit more sense. But the distances are now all been scaled also. On the right, these axes are approximately, roughly -2 to 2. So any kind of algorithms based on distance would treat these variables symmetrically, right? And wouldn't kind of overemphasize monthly income. Here's another example. We have more categories now. So we have customer IDs, we have ages, which is a number, we have student status and city, which are just labels, and then we have income and defaulted like we have before. So we want to dig into this and see if there's any pattern that relates like employment status to other aspects of our data set. So a naive ordinal encoding, so like replacing these labels with just numbers like we talked about initially, is naive. And this is an anti-pattern. There should be an X over here also. This is a bad thing to do. So I'm just going to say, well, student should be labeled 0, part-time is 1, full-time is 2, and so on. Okay? And then we're going to take a copy of our categorical data. We'll call that naive for now. We will have a new variable called employment code. And then what this is happening on the right, on line 10, we're saying we'll take the employment status, these labels, and then provide a mapping of those labels to numbers, and then store those numbers on the left-hand side here in the employment code variable, right? So we have the original data in df naive. The employment status is student. Map naive map just says look up the label here in this naive map, and then replace it with a number. So student is 0, so 0 gets written into the column employment code. Okay. Full-time is the next element. Map that label according to naive map. Well, full-time is down here. That should be a 2, so write a 2 to the employment code, and that's what line 10 is doing. And then on line 11, I'm just basically printing this out so I can see it, to see everything makes sense. And yeah, according to our naive mapping, everything makes sense. Now, this has the warnings we talked about earlier. If the categories are ordered on a line, which means that you can kind of go from being a student to being part-time to full-time to unemployed to retired, and that linear ordering doesn't necessarily always make sense. Similarly, the distance between pairs is suddenly made meaningful by these numbers, right? The difference between someone being unemployed and full-time is a difference of 1, and that's the same difference as being full-time and part-time. The difference is 1. Is that meaningful? Is that distance something meaningful that I want to encode in any kind of future modeling that measures distance between points? Almost certainly not. So yeah, distance-based models, linear models, we're going to see a lot of. This will learn patterns from this numerical structure, which is fake, like it's totally arbitrary. If I just ordered these things differently, then the numbers would have come out totally differently. So there's nothing about reality that gave me these numbers 0 to 4. Rather, we can do something called one-hot encoding. Pandas gives this to us for free. I wouldn't worry about this too much over here. This display is just here to kind of give me some visuals. Again, I have my columns, my categorical columns, and I want to keep everything. I have this function over here, which basically has colors in the blocks. Again, this is nothing to do with this class, but if you care about just learning Python and visualization, the function from line 9 to line 14 is just doing the coloring that you see here. But what's really happening here is that I'm taking my encoded data and providing the coloring that I specify in color blocks, and then I display it. Okay. So what that code gives us is it converts employment status to like emp, and then the label full-time, part-time, whatever. It takes everything under city, and it prepends the word city in front of it, and then its value. So whereas previously the column city had values Halifax, Truro, and Sydney, now I have new variables, city underscore Halifax, city underscore Sydney, and Sydney underscore Truro. Those prefixes, city underscore, I get from line 5, and it's applied by this getDummies function to all of the possible values in city. I think the important conceptual thing here is just to see how I've converted the labels, these labeled things, into one-hot vectors, which I previously called 0 and 1 vectors. Here I have Boolean values, false and true, but the relationship is completely identical, right? So this first person customer ID 101 was a student. You can go back and confirm this yourself. And now this little blue region over here is sort of the one-hot encoding for that label. Are they full-time? No. Are they part-time? No. Are they retired? No. Are they a student? Yes. Are they unemployed? No. So I've converted this label into a one-hot encoding 00010 with all of the benefits that conveys. Where is this student located? Are they located in Halifax? Yes. Are they located in Sydney? No. Are they located in Truro? No. So the city variable has been converted to true, false, false, or 100. Okay, so now there's no fake ordering between any of these things. Now the difference between Sydney and Halifax and Truro is just a binary kind of difference. And you can remember that that three-dimensional graph we saw earlier, where these points were just on these axes. They're maximally different from each other. That's kind of what we want. There's no ordering, and the distances don't mean anything. Every data point is equally, every label is equally equidistant from all the others. So now we can bin age into groups and look at the default rates. So we have our bins. Our bins are like everything less than 18, everything between 19 and 30, everything between 31 and 45, and everything above 80. And our labels are going to be young, mid, and senior. Okay, so actually, so these are I misspoke. These bins are the boundaries. So we have 4 boundaries because we have 3 regions. Let me just see if I can move something around again. There we go. So young would correspond to the bin between 18 and 30. Mid would correspond to the bin between 30 and 45. And senior would be the bin between 45 and 80. Obviously, there's some problems now here that you might have to deal with. So what happens if someone comes along and they're 17? Or what happens if someone comes along and they're 81? Do you label them young or senior? You're going to have some logic in your code to help you out there. Regardless, I'm taking my categorical data, I'm copying it into this thing called dfbind, and then I'm going to make a new column called age group. And this function over here is a pandas function called cut. It's a call from the pandas library, pandas PD, called the cut function, and then take the data in my data frame under the column age, and then cut it, or in other words, bin it, according to the bins defined in the variable bins over here. This bins equals bins is a little bit confusing, potentially. Everything to the left here is sort of like the label that this function expects, so it's always going to be bins. And everything to the right is going to be whatever variable I have in my environment, which in this case is just bins. If I called this variable on line 1 bins 0, then it would be bins equals bin 0. And labels equals labels, and so on. Okay. This is a bit confusing. In my point of view, this is not like how I would like to code things up myself, but this is sort of standard practice in Python, so we're going to go with it. And then regardless, I want to, so now I've cut the age data, the numerical data, down into these bins, and I've stored those bin labels, which I get from here, and I've specified here. I've stored all of those labels in this new column called age group, and now just show me, age group, and whether they've defaulted or not, and then I print this up automatically. We have age, 22 is young, 35 is mid, 60 is senior, and for every data point I have they're defaulted here also. So maybe you can check out a few things. You can see is there any kind of relationship between the age group and whether they've defaulted or not. It might be hard to look at whether they've defaulted or not in the specific age. 22, 35, 41. Especially if I have thousands and thousands of these things, it can mean any kind of high-level interpretation challenging. But I've binned age by groups, and then now if there's a pattern or lack of a pattern, it might jump out at me. Okay, you can see quickly that, well, for the 3 defaults I can see so far, 2 of them come from senior citizens and 1 comes from a young person. Okay, so it's not uniform, it's not unanimous, but it might be a little bit easier for me to intuit what's going on here with defaulting than having to look at 45 and 29 and 60. Okay, so it's a little bit for your own intuition, and it's going to be a little bit useful for models we're going to see a bit later. So we can compute default rate by age group. So once again, here's a group by function we've seen several times. Let's take all of our df bind data. Now we can do group by. I could not group by a number, but I can group by labels, right? So what am I grouping by? Well, I'm grouping by age group, these labels. So like we saw in previous modules, I have one, cluster of data, one separate, a silo of data for young people, a separate one for mid, and a separate one for senior. And I want to just look at whether they've defaulted or not. So in each of these groups, just measure like the defaulted column. Okay, so now I have just the defaults within each of these 3 groups. Computing the mean on a binary variable, like we've talked about earlier, is essentially just computing the proportion of data points that are positive. If this doesn't make sense to you, I'm happy to talk to you on why that's the case, but you just sum over all the data. You get all the ones, you divide by all the total number of data. This is the proportion of ones divided by all of the data. So hopefully that's obvious. I'm going to rename these averages default rate, and then I'm going to reset the index, that's the ordering, and then that's going to be stored in group default. And then I'm just going to now look at group default. And here I get it. I have the default rate for young, mid, and senior. I have those groups because I called the group by function. And now I have these averages. So half of young people default, none of the mid people default, and about 2/3 of the senior people default. So I'm starting to get some useful information, some useful statistics broken down by group. We can go ahead and plot things. Nothing interesting happening here really, but here's the code for you anyway, just again to make sure you understand what's going on under the hood. Here's just a visualization of what we saw a moment ago. This might convey extra information to you, it might not, but here's a visual that goes along with the table. Even with a small amount of data, we can start to see whether some patterns are emerging. Obviously, I wouldn't trust a data set with so few data points, but I'd want to collect more data, but at least we're starting to get somewhere. In real data, we need more rows, many, many more rows ideally. And we need to have some measure of uncertainty. This is getting way ahead of ourselves, but it's one of the most fascinating things in data science, in information theory and machine learning, which is can you actually measure how uncertain you are about your statistics? So we might come back to that later in this course. A little bit of ethics as usual. Even when we're doing pre-processing, we need to think about what metrics are going to matter later. Okay, so for the credit union scenario, there's a couple of risks. The main risk for us is going to be approving too many risky loans. Okay, there's too many false negatives. We think someone is safe, but they're not. So they're going to default, and then we're going to basically be throwing money away and never going to see those dollars again. So some metrics we might care about are things like recall for positive class, precision, and accuracy. We'll talk We'll talk about those in future modules. But just to highlight, we want to have a couple of statistics we can have to measure, how often we catch these defaulters, and how many people we accuse of being defaulters are actually defaulters. The choices we've made, the pre-processing choices we've made, can change how easily a simple model will separate these groups together. Okay, so before we had data on all kinds of different ranges, and if we wanted to learn a model to separate these groups out, if we didn't do the pre-processing, it could be very difficult to come up with these kind of categorizations. This is more of an empirical thing. This is an observation that you're going to get when you do more and more experiments, but it's something that keeps coming up. How stable the decisions are across groups. So whether there's a consistent pattern in a particular city or in a particular employment type or a particular age range is something that we want to obtain from data. So later on, when we actually train models to make predictions, this person looks like they're going to default, this person looks like they're not going to default. If you train the model with and without the scaling that we've done, then we're going to see whether or not that has any effect. And spoiler alert, it does. And whether or not that has an effect in terms of these measures, how accurate the model is, so to speak, will be increasingly clear to us. So that's all good. There's some risks here, though, right? So in a lot of cases, we might be forced to, or we might want to remove certain information from the data set because we're ethically obliged to. Like, for example, somebody's race, for example, should not factor into whether or not we give them a loan or not. Unfortunately, sometimes there might be a signal, maybe the past data that a credit union had, they gave more loans to a particular ethnic group and fewer loans to another ethnic group. And you could remove information, specifically ethnic group column with all the labels. You could just remove it and throw it away. But if you keep postal code, or if you keep city, we had Halifax, Truro, Sydney, it's possible that statistically there may be more or less people from different ethnic groups in different cities or different postal codes. A lot of cities have a little region that is called, X town for that group, Little Italy, Chinatown, and so on. So if people live there, the chances of them belonging to that ethnic group might increase a little bit. It might not, obviously, but it might. And therefore, if you're learning a model that only has postal code, that's kind of a way that information leaks in about their ethnic background. So even though you've removed information, you removed the column ethnic group, information about the ethnic group has snuck in. And so on. So a lot of these proxy variables that represent other variables, kind of because they're correlated with each other, can be a risk. And overly granular bins, so very tiny groups we talked about, can also make individuals identifiable. If there's only one person in a data set who has a particular age, then it doesn't matter if you remove their name and other information about them. Like if you wanted to, you could trace back behind the scenes information about them and say, well, there's only one 25-year-old in our data set. I know that person is person so-and-so, and now I know everything about their income and where they live and et cetera, whether they've defaulted or not, which is a huge ethical and legal risk. So there are mitigations against it. Data sheets are something we'll talk about more. This is basically documenting features, its source, why it exists. Documenting everything is always going to be important to us. Performing checks, so making sure that the information about ethnic background hasn't leaked into other variables by accident. And then, avoiding features basically whose role only encoded. Historical discrimination obviously is something we want to avoid generally. So quick checks. Please go to the questions on the slides and write these down and ideally submit them. And see you next time.